Let's talk today about induced current in a wire. Now, we've previously talked about how a wire with a current induces a magnetic field. Okay. This time we're going to have a magnetic field plus a wire with loops, and that's going to induce a current. So what am I talking about? Basically, if you have a magnetic field, this is how you draw a magnetic field. You should have got that from the textbook. If we have a magnetic field and we move some coiled wire through it, and move it like maybe in a direction perpendicular to the field, so we like move it like either through or maybe back and forth, different things. When we have that and we move it through there, it creates something called electromagnetic flux, and that's EMF. And it's basically voltage that it creates. Electromagnetic flux is measured in voltage, measured in volts. So here's the formula. I'm just going to jump right in. Now, this is called Faraday's law of induction. I think it only has one R. Faraday's law of induction. Let me switch colors. Okay. Faraday's law of induction says, and this is a slightly different form that I'm going to give you than you'll see in your book, or if you look it up on Wikipedia or whatever. Basically, Faraday's law of induction says that the electromagnetic flux is negative the number of loops times the area of the loops times the change in the magnetic field over the change in time. So n is the number of loops, a is the area of each loop, and then b is, of course, magnetic field, and t is time, obviously. Okay, so what we can do is we can figure out the electromagnetic flux, which is, again, essentially voltage, if we move something through a magnetic field. Now, what I mean by time is the time spent moving through the field. All right, and this is also going to assume that it's something like what we have here, where the coil is perpendicular to the direction of the field. So if I had like, maybe I had like a box, a coiled box or something, then the field would be going this way. We're assuming that for this formula that the coil is perpendicular to the field. And you'll see it said that way in all the problems that I'm going to ask you to do. So we're sort of simplifying this a little bit, but I don't think you guys will mind too much. So basically, we can do this to find electromagnetic flux, which is practically voltage. Now, when I started talking, I was talking about current. So how can we find current? Well, guess what's still true? V still equals IR. And which, actually, in this case, EMF equals IR, meaning that to find current, we're just going to have to do I equals EMF over R. So you're going to have two different types of problems. One that's just straight up looking for electromagnetic flux, and then you're going to have others that are looking for current. It's not going to be difficult. You just plug into this equation pretty much. Now don't forget that delta B means BF minus BI. No, just don't forget that. Okay, now one other quick thing. Notice this negative symbol here. Just believe it, don't just drop it, but all that negative refers to is the direction of the current. So you're going to often end up with negative voltages, and that just means that there's voltage in the other direction. So don't just drop it off, but don't get upset if you end up with negative current and negative voltage. That actually does make sense. It just means the other way around the circuit. So this should be pretty simple, like I said. Just plug in and trust your instincts.